This video will finish up Chapter 7. We'll start off doing a practice problem on alkene addition, then we'll talk about carbocation structure and stability. Remember, that's an intermediate in these alkene addition reactions. We'll talk about something called the Hammond postulate and how that helps us to determine what a transition state looks like. Then we'll get into carbocation rearrangements. This is a tough subject that students find difficult, so you want to make sure that you have your coffee for this. You may even need to pause the video and come back to it. And then I'm going to finish up with an overview of the 4 types of mechanistic steps. So what if I asked you to figure out the alkene required to prepare the following product? So you know that an alkene plus HX will give you a product where you've gotten rid of the alkene and you've created 2 new bonds, one to a hydrogen and one to a halogen. So the halogen in this case is iodine, so the reactant must have been HI. And we know that the halogen goes on one of the 2 carbons that made up the starting alkene. So if we look at this product, we know that the iodine is on this carbon, so that carbon was in the original alkene. But was that carbon double bonded to this carbon, or this carbon? Well, let's draw out the possibilities and then evaluate it. So that's one possible alkene that we'll evaluate. And another possible alkene would be this alkene that would be formed from a double bond between those carbons. And then the other alkene, that's actually the same compound as the one I drew initially. It's just flipped over. So these carbons, if I drew a double bond to either carbon there, I would get the same starting material. So let me just consider these 2. So when I add HI, the H goes on the carbon with more H's, and the I goes on the carbon with less H's. So if I reacted that alkene, the iodine would go here, and the H would go there, which now does look like the product. So that could have been the starting alkene. But what if I reacted my other possible product? So here, this carbon is the one with more H's, and this carbon has less H's. So the H would go on to that carbon with more H's, and you would end up with this product, which is identical to what I just drew. So what does this tell me? It tells me that either alkene, when reacted with HI, would give me the product that you see here. So sometimes I give you a reactant and then I ask you to draw the product, but I could also give you the product and have you figure out what was the starting material, and it's like a complex puzzle for you to solve. So why don't you try this yourself? So here is the product, and this came from some alkene plus HBr. So pause the video and see if you can figure out what alkene that would have come from and put your answers in the chat. You can either paste an image or you could just write the name of the alkene. So remember, this is the carbon with the halogen attached. So you know that that carbon was double bonded in the starting material. The question really then is just, was it double bonded over here or over here? So you could draw out both of those alkene options and then do the reaction, have it add to HBr, remembering that the H goes on the carbon with more H's and the Br goes on the carbon with less H's. Now the intermediate formed in these alkene additions are carbocations. A carbocation is planar because it's sp2 hybridized. So it has 3 sp2 hybrid orbitals forming these sigma bonds, and then it has an unhybridized p orbital, which is empty, that extends above and below the carbon like this. Now, stability of a carbocation increases with increasing substitution. So a methyl would be the least stable, but as soon as you add one R group, that becomes more stable, 2 R groups even more so, and 3 R groups even more so. There are 2 reasons that highly substituted carbocations are more stable than less substituted ones. The first reason is inductive effects. What does that mean? That means that these alkyl groups attached to the carbocation carbon are inductively sending electron density to that electron deficient carbon. So inductive effects occur through sigma bonds, so it's a shifting of electron density through sigma bonds. And you can see from these electrostatic potential maps that the blue color is not as large as we increase in stability, and the blue relates to positive charge. So over here we have 3 alkyl groups. These 3 methyls are inductively sending electron density toward that positive carbon, which is stabilizing. The second reason is that hyperconjugation, which I introduced last time. So with hyperconjugation, the CH bonds are overlapping with the empty p orbital on the carbocation carbon, and that has a stabilizing effect. Now, carbocations can undergo something called a rearrangement that comes in 2 flavors. We have the 1,2 hydride shift and the 1,2 methide shift, also called a 1,2 methyl shift. So in this, we have a hydrogen moving over with these 2 electrons. And so it's moving over just 1 atom over to the carbocation carbon. When it does that, the positive charge moves to where that hydrogen atom came from. Here we can also do that with a methyl shift. So we can take an entire CH3 group and we move it along with the 2 electrons. So we have a normal headed arrow here. We move it with its 2 electrons to the other carbon, and then the positive charge also moves. So importantly, shifts can only occur from an adjacent carbon, and they will only occur if a more stable carbocation results. So this carbocation is a secondary carbocation. It's secondary because it's attached to 2 other carbons. But when we do the shift, this becomes tertiary, and that's more stable, so that's good. Over here, this carbocation is also secondary. On this adjacent carbon, there aren't any hydrogens to move, but there is a methyl we could move. So we're going to shift over that whole methyl group, and as a result, we get a more stable tertiary carbocation. Whenever you encounter a carbocation, you must consider if a rearrangement, either a hydride or a methyl shift, will result in a more stable carbocation. So for example, what we have here is a secondary carbocation. It's attached to 2 other carbons, which is why it's secondary. And the question is, could it rearrange to a more stable carbocation? If it can, it will. So to determine this, you start by identifying the hydrogen atoms and or the methyl groups on neighboring carbon atoms. So here are the neighboring carbon atoms to that carbocation. And this carbon has 2 H's, the carbon on the right has an H and a methyl. So those are the things that could be shifted if that shift will result in a more stable carbocation. So next you have to determine if shifting one of those groups does result in a more stable carbocation. And it turns out that if you shift this hydrogen with its electrons, you get a tertiary carbocation as a result, which is more stable. If you were to shift that hydrogen, you would get a secondary carbocation, which is no better than what you started with. And if you instead moved the methyl, so if you tried to shift the methyl, you would get this structure, which is also secondary, so that's also no better than what you started with. So we're looking for an improvement in our life circumstances. And going from secondary to secondary, that's a lateral move, That's not an improvement. It's not going to happen. But going from secondary to tertiary, hey, things are looking better, so that will happen. Carbocation rearrangements are generally irreversible, and that's because there's no driving force to go from a more stable compound to a less stable compound. However, there is driving force to go from a less stable to a more stable. Here is an example of a reaction. So if we have 3,3-dimethyl-1-butene and we react it with HCl, first the H goes on the carbon of the alkene with more H's, and that gives us a secondary carbocation. So now we have to stop and ask ourselves, could a hydride or methyl shift occur that would give us a more stable carbocation? And the answer is yes. In this case, here are our neighboring atoms. We could move one of the methyls on the left over and get a tertiary carbocation, which is better. And then in the second step, the chloride attacks the carbocation, and you get this as the major product. You don't see much of that. And hydride shifts aren't only done in the lab, they actually occur spontaneously in biological systems. So this is one small step from the biosynthesis of cholesterol, which involves a hydride shift. Now pause the video and determine if the following carbocations A, B, and C will undergo a rearrangement. If yes, indicate whether it will be a hydride or methyl shift and which neighboring carbon the hydride or methyl shift will be shifted from. Now Dilly wanted me to remind you that in approaching this problem, you should look at the neighboring carbons and determine what hydrogens and methyls they have, and then ask yourself, if you use one of those hydrogens or methyls and perform a shift, will that result in a more stable carbocation?